Hello, and today we're going through all the practicals for A-level physics, and let's get started. So first we're going to start with the standing waves practical. So first, let's draw the apparatus. We have the bench first, and we have the signal generator, which is connected to a vibration transducer over here, which is connected to a string of a length L, which is also connected at the end of the bench to a pulley, like this. And then at the end, there are a few masses being hung off the pulley, like this. This is the masses, the pulley, this is the vibration transducer, and the signal generator. So now let's label the diagram. So we'll have the signal generator over here. This is the vibration transducer, this is the string, and this is the pulley, and these are the masses. And you have tension pulling the string down like this, tension, T. So now let's go through all the steps for this practical. So the first step is to find the mass and to find the length. And then we'll use the mass and the length to find the mass per unit length, which is mu, which is equal to m/L. And then we would set up the apparatus from before and work out the tension using the masses. So the masses of the blocks from before, so these masses over here, multiplied by the gravitational field strength is equal to the tension. Because if we look at the diagram from before, we would have mg going down like this as the weight of the mass, and we would have an equal and opposite force of tension going up. So we can equate mg is equal to T. So now we turn on the signal generator and we'll vary the frequency until we find a standing wave, which would look something like this, where you have nodes over here, each one of the places where the string doesn't move, and these are the antinodes over here, each one of these. So these are the nodes, and these are the antinodes. And once you do that, you have the choice of, so depending what they ask you on the exam or in the practical, you have a choice of either doing F, which is the frequency of the first harmonic. So you could either do F against L, F against T, or F against mu. And for each of these experiments, you would either change the length of the spring, you would either change the tension, or by changing the weight of the masses at the end, so you would change the amount of mass here, or you would change the type of string. And once you find the frequency at which you have a standing wave like this, to find the fundamental frequency, so the frequency of the first harmonic, you would have the number of antinodes, so you have n antinodes, and if you have the frequency that you set your signal generator as F, large F, to find the frequency of the first harmonic, you will do F over the number of antinodes. And remember, for each one of these, if you choose one of them, remember to keep the rest of the variables the same. So now let's go over what results you expect to see. So if you have a longer string, you would have a lower resonant frequency. If you have a heavier string, so a larger mu, you would get a lower resonant frequency as well. And if you get a looser string, so less tension, you would get the same thing. You'll get a lower resonant frequency. So if we look at the equation of the first harmonic, we would get F is equal to 1/2L, which is the length of the spring, times the square root of the tension divided by the mass per unit length. And the results should be consistent with this equation. Now let's move on to the next practical, where we have two practicals, either the double slit or the diffraction gratings practical. So for the double slit, you would have a apparatus of a laser like this, which you shine light onto a double slit like this, and then you would get waves coming out like this, which diffract onto a screen over here, and you'll get a combination of light and dark fringes. So you'll get light fringe here, light fringe here, and light fringe here. And let's go through the steps of this practical. So first, you could use two coherent sources, so different to this one, or you could shine a laser through two slits, which is what we would do in this setup here. Then we would shine it onto a screen like we did over here, and make sure that the slits are similar length to the wavelength, so that you get most diffraction. You can do this experiment also with microwaves, where you have two transmitter cones, so something like this, and they radiate microwaves, and they also cause a diffraction pattern. And what you can do is use a probe on the other side and move it up and down to find that you will get a difference in amplitude of readings. So you get high amplitude here, and you'll get lower amplitudes on the side, something like that. And for these kind of experiments, because we are working with lasers, we would have to consider the safety. You would never shine towards a person, wear safety goggles, avoid reflective surfaces, and turn the laser off when it's not needed. Now, if we were to do diffraction gratings, we would have this very similar experiment to this one, but instead of using a double slit, we would use a diffraction grating. So it would look the same as this, but instead over here, we would have a diffraction grating instead of a double slit. So we have multiple slits in between. This causes many beams, which causes to reinforce pattern. You would get a sharper interference pattern, which is better for more accurate measurements. So for finding G by 3/4, this is the next practical, let's draw the apparatus for this. So you would have a electromagnet at the top like this, with a coil around it, and you have a ball bearing like this here. Then this would be connected to a circuit, a battery over here, and you'll have a switch over here, which is connected to the rest of the circuit over here. And then you have another part of the circuit down here, where you have a trapdoor, and next to a timer over here, connected to this part of the circuit, like that. So this is an electromagnet, this is the ball bearing, this is a battery, and this is a switch. So now, first, let's go through all the steps. So first step would be to measure the height from the bottom of the ball bearing to the trapdoor. This part here to the trapdoor here. And we would measure this as H. So we'll flick this switch, and simultaneously it will stop the electromagnet from running, so the ball bearing will no longer be attached, and it will start this timer over here. The next step is that the ball falls, and when it hits the trapdoor, the circuit breaks, and then the timer stops again, recording the amount of time. Then we would repeat this experiment and calculate an average time taken. And you can also repeat with different heights. So you can repeat either the same height or different heights. So you can have a similar version of this experiment. You won't have the same circuit, but you can have a similar version of it. and a lot of the steps are pretty similar. You just have to adjust for the apparatus they give you. But once we have all our data, you can draw a graph to find G. So the graph would look something like this. You would have H like this, so H on the y-axis, the height. If you have different heights, times squared on the x-axis, then we can plot the graph, so you have points like this, and we can draw a straight line to calculate a gradient. And using this graph, we'll know that the gradient is equal to h over t squared. Using suvat, so s is equal to ut plus a half at squared. Because we start with an initial velocity of 0, so u would be 0, we can get a new equation of s is equal to half at squared. And if we rearrange, so we'll get s as the height, so we'll get h, but it will be a minus height, so we'll get a minus h. And then we will have times by 2, so we can get minus 2h. And then we can divide by the t squared, so we'll get t squared is equal to minus g. And then here we have the two minuses, which we can cancel out. And using the gradient, which we said was h over t squared, so if we do gradient multiplied by 2, we would get g. Now, how would we make the experiment more reliable? So there's many ways we can do that. We can use a small plus heavy ball bearing, so we can reduce air resistance or drag, and also reduce its effects by making it heavy, because the ball will have more inertia. Another way we can make this more reliable is by using a computer, which would be a lot quicker at taking readings and can take more readings than humans. So the largest uncertainty of this experiment comes from the ruler, because you have a plus minus 0.5 millimeter of uncertainty. So now let's move on to the next experiment. Now we are moving on to the Young's modulus of a wire. So let's draw the apparatus. So we would have a clamp over here, and we would have a bench. So there's different ways of doing this experiment. Well, I'm going to do it this way. The other one is similar, but it's just vertical. And then we'll have a pulley over here, and we'll have a bench connecting everything. We'll have a ruler on the bench, and on the wire we would have a marker like this, and the rest of the wire is connected to a mass at the bottom. And let's label it. So here we have a fixed end of a wire. This is the bench. This is a ruler. This is a marker on the wire. We've got the pulley here and the masses or weights. Now let's go through all the steps. So the first step would be that we would have a test wire, which should be as thin as possible and as long as possible. Why? So we would have a longer extension. And if we have a longer extension on the wire, we would have a larger value of L. So say X would be larger, and our change in X, so the percentage uncertainty, would decrease. So now point 2, we would have to measure the cross-sectional area using a micrometer. So we would need to measure the diameter in different places of the wire. So we would measure around here, for example, here and here, and use the measurement of the diameter, so find diameter, to use diameter divided by 2 all squared times pi to find the cross-sectional area. And we use a micrometer. And we are assuming that the wire is circular. Then the next part is to make sure that the wire is fully extended by adding the smallest amount of weights that makes the wire go straight. Then we would have to measure the distance between the fixed end and the marker on the wire. And this would be the unstretched length, given that we've used the smallest amount of weights to make the wire straight. So the distance between here and here would be our unstretched length. So point 4, find unstretched. For the next step, we will need to increase the weight of the wire. So add more weights, which causes the wire to stretch and the marker will move. The sixth step, we would increase the weight in steps, recording the marker at each length and measuring the extent to find the extension, which is the difference between the reading and the unstretched length. So increase the weight in steps, and then we would take a reading and then find your extension for each of the amount of weights, which can be found using the new length, so the length that you recorded, minus the initial length, which is equal to the extension x. Now, using your result, you can calculate the stress and the strain of the wire. You can find your stress of the wire. So stress is equal to the force times over the area, which you can do mg using the tension over the area. And you can find your strain, which is just the change in x, which was your extension, which we found up here, over the natural length of the wire. And using the values of each of these, you can plot a stress strain graph, which will look something like this. And you'll get a straight line like this. And the gradient would be stress over strain, which is equal to the Young's modulus of the wire. So now let's move on to the next experiment. Now we would have to find the resistivity of a wire, which is a very similar setup of the previous experiment we just did. We would have an apparatus with a power supply connected to both sides, so like this. And then we would have an ammeter over here. And we would connect this to a wire, so you can draw in red, a test wire, and we will have a ruler underneath it. And you would have a flying lead over here, which connects to the rest of the circuit, like this. And then you would have a voltmeter across it. So this is the apparatus, where you would have the power supply over here. You would have an ammeter. You would have the voltmeter. You would have a ruler. And this is the flying lead. And this is the test wire. And that's the whole apparatus. So now let's go on to the steps. First, what would we need to find? We would need to find the diameter of the test wire at 3 different points, very similar to the previous experiment we just did. And we would take the average and divide by 2 using the area. So find diameter at 3 different places. So say you have the test wire that looks something like this. You would find the diameter at points over here, here, and here. These 3 places. And you would measure the diameter and use d over 2 squared pi to find a cross-sectional area. And find an average, which you can use as your value, and you also have an uncertainty because of the different values. Then we would clamp the test wire to a ruler with a circuit attached to the wire, which is basically the apparatus we had before, and would have to make sure that the wire is attached to the ruler at where it says 0. So this is 0 over here. Then we would attach the flying lead to test a wire at different increments. And we would record the voltmeter and the ammeter and use V equals IR to find the resistance. So record I and V and use R equals V equals IR, which we can rearrange to get R equals V over I, to find resistance. Then we will repeat this for several different lengths, and we will plot the results on a graph which looks something like this. You would have resistance against length, and the graph would be something like a straight line like this. And using the equation of resistivity, which is rho is equal to RA over L, we can rearrange this equation to get R rho over A, which is equal to R over L, which is the same as a gradient. We can get rid of this part here, ignore this part, which is the same as R over L. We can just say rho is equal to the gradient times the cross-sectional area. So we would find our gradient with an uncertainty by using the maximum and minimum gradient and multiply it by the cross-sectional area, which we found using the diameter before, and we would find our value for the resistivity. To make this experiment more reliable, we would have to take some things into consideration. So the resistivity, so rho, depends on temperature. To remove random errors, we would use small currents, and we would take breaks between readings. We would do these two things because they would prevent the temperature from getting too high, so the temperature would stay low. Now let's move on to the next electricity practical, which is investigating internal resistance and e.m.f. So first, let's draw the apparatus as always. So we would have a battery like this with an internal resistance like this. And we would have an ammeter attached to the circuit in series and a voltmeter as well in parallel to the circuit. And after we would have a variable resistor to act as our load resistance. So this is the battery with this internal resistance, and this is the ammeter, and this is the voltmeter, and this is a variable resistor, which is a load resistance R. Let's go on to the steps. First, we would vary the current in the circuit by changing the load resistance. So, because we have a variable resistor over here, we can change the value of R. So we'll change R, which will change current. We will measure I and V. I'll repeat this with different current values or different R values. And now you can draw a VI graph. And you would get a graph that looks like this, which is a straight line with a negative gradient. The y-intercept would be the e.m.f, and the gradient would be equal to minus of the internal resistance. And we can actually derive this whole thing from a formula. So we will have the e.m.f being the sum of voltages, V plus small v, which is the lost volts. And we can represent small v as the current, because the current is the same in series in the circuit here. So the current would be the same. So the current times the internal resistance using V equals IR plus I, small r. Okay, and now we can rearrange this equation to make V the subject. We would get V is equal to E minus IR. And if we compare this to an equation of a line, we would get y is equal to mx plus c. We would see that v is equal to y, and I is equal to x. So our gradient, if we compare coefficients, our gradient would be minus r, which is the same as m, and our y-intercept would be epsilon, which is our e.m.f. So that we have derived the values of this equation. And with this, you can just find experimentally derived value of e.m.f, and experimentally derived value of the internal resistance using both of the gradient and the y-intercept. Now let's move on to the next experiment, which is a mass on a spring or a simple pendulum, and these are simple harmonic oscillators. So you can do either one of these. So we're going to go through both. So first you would have let's draw the apparatus for the mass of the spring. So you would have a clamp and a stand, something over here, on a bench, like over here, and you would connect to this a spring, and you would have a mass connected to it, and you would have a ruler beside it, and that is it. And let's annotate this. So we would have the ruler, the spring, the masses, the workbench, this is the clamp, and this is the stand. And now let's go through the steps. Number 1, pull the masses down a set amount, and this will be your initial amplitude. So you would pull them down here and say this. If you pull them down all the way down here, this would be your initial amplitude. Now the next step would be to cause them to oscillate in simple harmonic motion, and you could investigate different factors affecting the period. You could either do time against the mass, time against the spring constant by using different springs, and for the mass one, you would change the amount of mass you put on the end, and you could do time against the amplitude by changing the amount of distance you put it from the center. And what you would find in each of one of the cases, you'll have to linearize the graph for each, but what you would find for all of the cases, using a linearized graph, if you have t squared against mass, if you have t squared against 1 over k, which is the spring constant, and if you have t squared against amplitude, you would get different graphs for each. So for the t squared against m, you would get a straight line graph like this. T squared against 1 over k, you would get also a straight line graph like this. However, if you have t squared against amplitude, you would get a straight line because it's independent of one another. So the time period of the oscillation is independent of the amplitude. So you would measure the period of oscillation as your dependent variable, and either mass, spring constant, or amplitude as your independent variable, and your control variables would be the rest. So say if you change the mass, you do not change the spring constant or the amplitude, and if you change either one of the spring constant, you wouldn't change the mass or the amplitude, and if you change the amplitude, you wouldn't change any of these two either. So now let's go on to the simple pendulum. You would have an apparatus that looks something like this. So you'd have either a pendulum like this from a fixed point at the top connected to a pendulum, and you will have a fiducial marker over here to measure the transition. And now let's go through the steps. So the first step would be to displace the pendulum by an angle less than 10 degrees, so you can assume simple harmonic motion. Then measure the time of multiple swings, and then find the average period by dividing by the number of swings. So this is the time of multiple swings, and now the third step is to find t, the time period, by dividing t over the number of swings is equal to time period. And then you can draw more graphs similar to the ones we found for the mass on the string. And you can change variables such as the mass, the length, or the amplitude of oscillation to find the relationship between them. If you plot the time squared against the length of the pendulum, you would get a straight line graph like this. if you plot the time against the amplitude, you would get a straight line because it's not related. And if you get the time period against the mass, you would also get a straight line because it's not related and is independent of one another. And if you look at the equations of a mass on a spring and a pendulum, you would have T is equal to 2 pi times the square root of m over the spring constant for the mass of a spring. For the simple pendulum, you would have T is equal to 2 pi times the square root of L times the gravitational constant. And as you can see from these two, that the time is proportional to the mass and the spring constant, as we can see from these graphs here. But it's not dependent on the amplitude. There's no amplitude in this equation. And if you look from these graphs here, you can see that the time constant is only proportional to the length and gravitational constant, and not proportional to or dependent on the amplitude or the mass of the pendulum. So now let's move on to the next practical. So let's go on to investigating gas laws. The first law is Boyle's law, so let's draw the apparatus quickly. And you would have an oil level to here, and you would have a pump connected to the oil and an oil reservoir. So let's annotate it. So here you would have the pump, you would have the oil reservoir here, and you would have the oil here with a sealed container, and you would have air sealed in here. So now let's go through the steps. So the first step would be to set up the apparatus with the oil and increase the pressure from the oil and watch the volume of the air decrease. So you would have this would be a measuring cylinder where you could measure the volume inside of it. You would increase pressure using the pump and watch the volume decrease. So your independent variable would be the pressure and your dependent variable would be the volume. Then the next step would be to record the pressure against 1 over volume, and you would get a straight line graph. So just by proving that it's a straight line graph, you've proved Boyle's law. And also by testing as well, you can multiply every value of your readings for P and V. And if you multiply each value, PV, you should get a constant for each of the ones. So you get PV, your first reading for PV, it would be a constant, and your second reading for PV would also be the same constant. Now let's do Charle's law. So let's draw the apparatus. You would have a beaker like this, and you would have a ruler, and near that ruler you would have a capillary tube with some sulfuric acid, and you will also have a thermometer here as well, and this will be filled up with warm water. Let's label the apparatus. So this would be the thermometer, this would be a ruler, this would be the capillary tube, which is sealed at the bottom, and this is concentrated sulfuric acid, and you would have near boiling water in here. So near boiling water here and sulfuric acid here in the capillary tube. And now let's go on to the steps. So the first step would be to see as the water cools. So you put in the near boiling water, and as the water cools, the acid should go down. And here you would take readings for temperature and take readings for the length of the column using the ruler. And you should be able to draw a graph of T and L, so temperature and the length. And you should get a straight line graph like this. Remember, Charles' law is temperature over volume, so T over V is equal to constant. And because our volume in this case, V, is equal to pi r squared L, which is a cylinder of the capillary tube here. So the volume is proportional to L, because all the pi r squared doesn't change because the cross-sectional area of the capillary tube stays the same throughout. So we do get a straight line graph because this is the same as temperature, which is proportional to something that is proportional to the volume. So we will still get a straight line graph, which proves Charles' law. Now let's move on to the next experiment. So the next practical is capacitors, and here the apparatus would be the same for each one of these, both of charging and discharging. So we would have a battery over here connected to an ammeter, which is connected to a resistor, which is connected to a capacitor, which can be polarized, so you can have a positive side and a negative side. And this is connected to the switch, and across the capacitor you could have a voltmeter, and on the other side of the circuit you just connect the rest. So when you have it through charging, you would connect it to the battery side of the circuit, and when you have it discharging, you connect it to the other side of the circuit. So let's go through the steps for charging a capacitor first. Let's go on charging. We'll first let the capacitor charge through connecting the switch this way, and take readings at regular time intervals of the current and the potential difference. Then the second step is when current equals 0, capacitor is fully charged. Now that you've taken readings for the current and the voltage, then you can draw plot graphs of I and V in terms of time. So you would get something like this. And the graph for current would look something like this, where it approaches 0. And the graph for the voltage will look something like this, where it approaches a value V0. And this is for charging. And for discharging, the steps would be, so the first step would be to use the same circuit, but you flip the switch this way, so you connect the charged capacitor to the circuit that only has a resistor, so the charge will flow and loses energy at the resistor, so it discharges. And then the same as before, read the current and the voltage over time. And when it's discharged is when V equals 0 and I equals 0. And this is when it's fully discharged. And now you plot the graphs again. So we said this was V0. This would be also I0 at the start. You would have something that looks like this for current, which is very similar to what we had. But for voltage, because you start off at V0, you're gonna have something like this for discharging the capacitor. And this is charging and discharging done. Let's move on to the next practical. Now we are investigating the inverse square law. So we would have a apparatus which uses a Geiger counter, and then you have a ruler and a radioactive source on increments of the ruler. So we have the ruler here, the radioactive source, the Geiger counter, and a distance between the two places, the radioactive source and the Geiger counter. Now let's go into the steps of this practical. So the first step would be to turn on the Geiger counter and count the number of counts of radiation background for 20 minutes. So then we would place the Geiger counter so it lines up with the start of the ruler. We would Record the number of counts every 100 seconds and divide by 100 to find the count rate, and repeat this 3 times for every distance that the radiation source is from the Geiger model tube. The fourth step would be to repeat for regular intervals on the ruler, and then once the experiment is finished, you would have to get rid of the source as quickly as possible. This is for safety reasons. And now correct your data for the background radiation and draw plots. It looks something like this. So 1 over the square root of the number of the count rate over the distance d. And we do this so we get a linearized plot. We get a straight line when we plot our data. And the fact that you've proven that this is the square line, you've proven that it is the inverse square law, because you have 1 over the square root of the count rate over distance, which adjusts for the inverse square law, causing it to be a straight line. So that should be your findings. Now let's move on to the next experiment, investigating magnetic flux density. So the apparatus will look something like this, where you have a top pan balance and you've got magnet, so you have a north, south, like this. And you have the same on the other side. And you have a wire going through them, and it will be connected to a variable resistor, an ammeter, and a power supply. So now let's label the apparatus. So we have the balance, we would have the power supply, we have the ammeter, we've got the variable resistor, and we have magnets over here, where the blue side we can say is the south side and the north side is the red side. And now let's go on to the steps of the practical. So the first step would be to set up the apparatus and zero the balance, so when there is no current flowing through the wire. Second step would be to turn on the power supply and measure the mass recorded on the balance and the current on the ammeter. The mass M on the balance, which can be used to find out the force exerted by the wire. So the third step is to vary the current using the variable resistor, and then repeat the step 2, so take multiple readings for I and M. Now you can convert your mass readings into force using F is equal to mg, and you can draw a graph now of force against current, and you should get a straight line graph like this, and the gradient of this graph is equal to b times the length, and you can find the length by taking measurements from here and here. So the length of the wire that is within the 2 points of the parts that are in the magnets. So you can take readings for that. You can take multiple readings and find a mean, so you can find the uncertainty with it. And then you can do gradient divided by the length is equal to the magnetic flux density of the magnets in the top balance. And this is from the equation F is equal to BIL, where we just rearranged F over I, which is the gradient, is equal to BL. And you can repeat this experiment using different forms. You could either change L, so make the length of the wire longer inside and shorter, or you could use different magnets to change B. And that's the end of this practical. Let's go on to the next practical, the last one. Angle of a coil in a magnetic field. So let's draw the apparatus for this. So we would have a alternating power supply, alternating current power supply. So it would look something like this. And this would be connected to a circuit with a resistor. And then you would have a coil, which is connected to the rest of the circuit. And in the middle, you will have a search coil like this, connected to an oscilloscope. So now let's label the diagram. So you have AC power supply for alternating current. You have a search coil over here. You have a protractor underneath here, which is to measure the angle. This is a solenoid. And this is an oscilloscope. Now let's move on to the steps of this practical. So set up the oscilloscope so that it only shows the amplitude of the e.m.f. as a vertical line like this. Then position the search coil halfway through the solenoid. So set up the apparatus basically and point it so that it's parallel. And then record its induced e.m.f. in the search coil using the oscilloscope. And keep rotating it 10 degrees until it reaches 90 degrees. Taking readings each time for the e.m.f. So if we imagine what's going on, we would have inside the solenoid, we would have flux lines that look like this, parallel, which would go through the solenoid like this. And if these are the field lines, if the coil has the most area, so is parallel to the field lines, so something like this, it would take most of its area would be exposed to the field lines here. So if it's rotated, it will become something like this. So the area would actually become smaller and will be exposed to less field lines. So when it's directly facing the field lines or parallel to the solenoid, that's when it has the most e.m.f. induced. And when it's at 90 degrees is when it will have 0 e.m.f. induced. And this is the end of all the practicals. Thanks for watching and good luck in your exam.